Scientists unite to explore why the universe exists. A Michigan State University researcher has helped lead a groundbreaking collaboration that could bring scientists closer to understanding how the universe came to be. For the first time, two of the world's largest neutrino experiments, T2K in Japan and NOvA in the United States, combined their data to gain new insight into neutrinos, the ghost-like particles that constantly stream through space but almost never interact with other matter. The joint analysis, published in Nature, offers some of the most precise measurements ever made of how neutrinos shift between types as they travel. This achievement lays important groundwork for future experiments that could reshape our understanding of how the universe evolved, or reveal that current theories are incomplete. Kendall Mahn, a physics and astronomy professor at Michigan State University and co-spokesperson for T2K, played a leading role in coordinating the project. By working together, the two experiments reached a level of precision that neither could have achieved on its own. This was a big victory for our field, Mahn said. This shows that we can do these tests, we can look into neutrinos in more detail, and we can succeed in working together. A cosmic imbalance. Why matter survived. Physicists believe that when the universe first formed, matter and antimatter should have existed in equal amounts. If that were true, the two would have destroyed each other completely. Yet matter somehow survived, allowing stars, planets, and life to form, and scientists still don't fully understand why. Many now suspect that neutrinos could hold the answer. These tiny, nearly massless particles may help explain how matter gained the upper hand over antimatter. Researchers are particularly interested in a process called neutrino oscillation, in which neutrinos spontaneously change the flavor or type as they move through space. Neutrinos are not well understood, said MSU postdoctoral associate Joseph Walsh, who worked on the project. Their very small masses mean they don't interact very often. Hundreds of trillions of neutrinos from the sun pass through your body every second, but they will almost all pass straight through. We need to produce intense sources or use very large detectors to give them enough chance to interact for us to see them and study them. How T2K and NOvA track elusive particles. Both T2K and NOvA are what scientists call long baseline experiments. Each one fires a focused beam of neutrinos toward two detectors, a near detector close to where the beam is produced, and a far detector hundreds of miles away. By comparing measurements from the two, researchers can track how neutrinos change as they travel. Although T2K and NOvA share similar goals, they differ in their distances and energy ranges. That makes the data complementary, and combining them gives scientists a more complete picture of neutrino behavior. By making a joint analysis, you can get a more precise measurement than each experiment can produce alone, NOvA collaborator Lyudmila Kalupeva said. As a rule, experiments in high-energy physics have different designs even if they have the same science goal. Joint analyses allow us to use complementary features of these designs. The neutrino mass puzzle. One of the biggest mysteries in particle physics is called neutrino mass ordering, determining which type of neutrino is the lightest. The answer isn't straightforward because each neutrino, flavor, is a blend of three mass states, and each mass state behaves differently. There are two main possibilities. In the normal ordering, two mass states are light and one is heavy. In the inverted ordering, the pattern is reversed. These arrangements influence how neutrinos and their antimatter partners, known as antineutrinos, change flavors. In the normal case, muon neutrinos are more likely to turn into electron neutrinos, while muon antineutrinos are less likely to do the same. In the inverted case, the situation is flipped. If neutrinos and antineutrinos behave differently, that would mean they violate charge parity, CP, symmetry, a principle that says matter and antimatter should mirror each other. This violation could help explain why the universe contains matter at all. What the results reveal: the combined analysis from NOvA and T2K does not yet favor either mass ordering. If the normal arrangement is correct, the data so far unclear about CP symmetry. But if future results confirm the inverted ordering, the findings published now suggest that neutrinos may indeed violate CP symmetry. If CP symmetry violation does not occur, scientists would lose one of their strongest explanations for why matter exists in greater quantities than antimatter. Either way, this joint study marks an essential step toward solving one of physics' most enduring mysteries. A global effort in discovery. While the findings do not yet solve the puzzle of neutrinos, they add valuable knowledge about how these particles behave and demonstrate what large-scale scientific cooperation can achieve. The NOvA collaboration includes more than 250 scientists and engineers from 49 institutions across 8 countries. The T2K team involves over 560 members from 75 institutions in 15 countries. The combined work began in 2019, drawing on 8 years of NOvA data and 10 years of T2K. Both experiments continue to collect new data to refine and expand the analysis. These results are an outcome of a cooperation and mutual understanding of 2 unique collaborations, both involving many experts in neutrino physics, detection technologies, and analysis techniques, working in very different environments, using different methods and tools, T2K collaborator Tomasz Nosek said.